Welcome to Chapter 12, which is all about kinetics. We're going to start by just doing an introduction of what kinetics is and talking about kind of setting the stage for moving forward through the rest of the course, talking about real reactions. So we've covered a lot of chemistry between General Chemistry 1 and so far even this semester. So when we have chemical reactions, we can write chemical equations, right? We can balance those chemical equations. We can work with stoichiometry, something like the recipe. If I want to react C3H8 with oxygen, how much oxygen do I need? I can fill that up. I can treat it as a gas. I can figure out what the volume of that is. I can work with the enthalpy. I could predict how much energy would come out of this reaction. I can tell that energy will come out because the delta H is negative. It's an exothermic process. We know that these molecules are real molecules. They have three-dimensional molecular shapes, bent, linear, tetrahedral. We have all these ideas that we can have. We're able to describe chemistry. And we're able to describe a lot of things in ideal cases, or what the perfect is, right? And if we remember in stoichiometry, we talked a little bit about, say, non-perfect stoichiometry when we talked about, say, limiting reagents, issues where things don't mix perfectly. But a lot of what we've talked about so far has been kind of in the perfect sense of how things should work, or in a theoretical world. But now, as we move forward, we want to kind of return to some of these ideas about chemical reactions, and we want to think a little more in depth or kind of question some of the ideas. For example, we've just kind of looked at chemical reactions and assumed, say, propane, C3H8, and oxygen. If we mix them, they just start reacting. We've just always assumed that they will just turn into products. But do they? If I mix propane and oxygen, do they just start reacting? What does it take to make that reaction start? If it starts, why does it become carbon dioxide and water? Why is that? If all we're doing is rearranging atoms into molecules, can I do the opposite? Can I react carbon dioxide and water to produce propane and oxygen? There's carbon dioxide and water in the atmosphere. Are they reacting just to form C3H8 in the atmosphere? So those sorts of questions are what we want to be getting at. What really happens in a chemical reaction, and kind of the whys and the hows that chemical reactions occur, and the reasons they occur in the directions that they do, and importantly, being able to make predictions and control chemical reactions. So kinetics, the study of chemical reaction rates. When I'm talking about reaction rate, I am talking about how quickly a chemical reaction occurs. And each chemical reaction has a rate that can be affected by external factors. Basically, the conditions that the reaction happens in are going to affect the rate of the reaction. What's the temperature of the reaction? How many reactants do you have present? Are there lots of reactant molecules, very little reactant molecules? What state are they in? Are you reacting something in the liquid or in the gas? Is it dissolved? What else is present? Are there other things that aren't reactants there? Are they getting in the way? Is there other chemistry happening? All sorts of issues and concerns like that. And so chemical kinetics are very important. Being able to know how quickly reactions happen is important if we want those reactions to happen. And so we're going to go through this chapter and kind of talk about how we describe chemical kinetics, how we simply talk about the rate of reaction, and a little bit as to what determines the rate of a reaction and how we can control it. So if we look at our propane example, C3H8 plus O2, we can write a balanced chemical equation. We can predict combustion products. We can go the whole 9 yards. But if I open the tank, if I just release propane into the atmosphere where there is oxygen, nothing happens. So when we can write a chemical equation, and if we mix the reactants, but the reaction doesn't happen, we would say that the reaction is slow. Or very slow in that regard. A chemical reaction that is very slow, it's so slow, it doesn't happen, right? You mix the reactants and it will take millions of years for them to react to become products. So that's important, that's useful. That's why we use propane as a fuel, because we can control when it starts to burn. If you do put a match in, say, your propane, all of a sudden you get a very fast reaction, right? Fire is in general a very fast reaction where if you introduce flame into the mixture, you can get the reaction to go and it doesn't stop, right? It just keeps going and it burns very, very quickly. And in fact, when you go from something that is burning to something that is exploding is because the reaction is happening so fast, it's happening faster than the speed of sound, right? So you have the reaction is propagating faster than sound waves travel. So that's how you can move from, say, burning into exploding. And so that is where, specifically detonation, and that is where and how, these speeds vary. So propane and oxygen, just under ambient conditions, say just in the atmosphere, if you release propane in your house, it won't burn, but you give it a little spark, and all of a sudden it goes real, real fast. So we can see the conditions, what else is present, really is going to affect rate. There are also plenty of times where we slow down reactions. So if you have, say, iron and you react it with oxygen, it will rust. And so you can take it and form it in rust. And generally, we spend a lot of time and effort trying to prevent this from happening because we use iron a lot. That's because iron rusting is degrading, right? Corroding. This material turns iron is a strong metal. Iron 3 oxide is a weak, brittle ionic compound that just crumbles. And so you lose that structural integrity. And so this is a slow reaction. It takes on the order of years if you have, say, iron that's exposed to the elements. But you can speed it up, namely water and salt work to speed it up. But that's why one of the reasons why we paint our vehicles is not only because it looks fly, but also because it protects the metal. You protect it, you prevent it from getting exposed there, and you can slow that down even further. There are things we know water would affect it. Salt really accelerates this. That's why in northern and cold climates, cars usually die a bit faster than in warm weather climates because of all the salt on the roads that degrades the bottom of the vehicle. You start to get structural issues. Things aren't really held onto the car anymore. And then there's problems that come from that. Even outside of that, if we take, say, something like burning wood. So say we want to burn a piece of wood. If I have a large, say, piece of wood, like a branch or something, and I try to burn it, it will generally burn pretty slowly. Again, when I talk about burning slowly, one of the things you can see, this part of the wood over here is not burning. All the fire is over in this region, over here. And so that corresponds to the fact that this piece of wood does not burn rapidly. Where the fire is happening is certainly burning quickly, but it's not propagating through the entire piece of wood rapidly. It is hard to get the entire log to burn on fire. If you have, say, if like you put a match up to a branch, it's not going to light on fire because that's a very slow process. It takes a lot of time to get going. If you take your wood and you chop it up into, say, pellets, all of a sudden it lights up very, very quickly because all you've done is changed the size. So we can control chemical reactions not just by affecting, say, the conditions or what we're trying to do the reaction with or temperature, but also just the shape and the pieces of chemical or pieces of matter that we are trying to react. Physical processes have rates too. Melting ice, for example. If you put a small little ice cube out on a table, or say a lot of ice, it'll melt pretty quickly. And if you go to, say, crushed ice melts even faster. Shaved ice, really, really fast. If you take a, say, giant block of ice and you put it outside in the summer, no, this dude is wearing a t-shirt, it's going to take a really long time to melt. It could be the same amount of ice, but you have one big block of ice that will melt more slowly than a lot of little pieces of ice. So chemical processes have kinetics, physical processes have kinetics, and that's something that we can control. If you want to keep your ice around for longer, you keep it as a big block. If you want to water down your drink real fast, put crushed ice in there. If you want to keep it not watered down, you get giant chunks of ice, big fancy cube ices and spherical ices. Those melt more slowly because they are bigger pieces of ice. Crushed ice melts real, real fast. Pour some water into a shaved ice and see how fast it goes. Finally, one of the most important places where we see chemical reactions is inside of organisms. And inside an organism, a living thing like you, there's a lot of chemical reactions that need to happen on command, right? If you want to do your mini band arm exercises, you're moving your arms all over the place, and you want to be able to control those. When your brain decides, all right, arm, move, all the chemical processes that run that need to happen in sync. They all need to happen at the same time. And importantly, you don't want those chemical reactions happening when it's not desired. So the chemical reactions that are causing, say, arms to lift need to not happen when it's not desired, and they need to happen immediately when the body is desiring it, when the brain is sending signals to lift your arms up. You have a lot of different chemical processes that need to happen on command. So importantly, the rates of chemical reactions in living things are highly controlled. They don't happen, chemical reactions aren't just happening willy-nilly inside of living things. That would lead to generally things like death. And so they're very slow rates when they're not desired. Very slow rate, remember, means it just really doesn't happen. The reactants are not becoming products. But when the organism wants something to happen, immediately every single chemical reaction happens in tandem. All of them go at the exact same time. So there are ways that organisms control those chemical reactions. There's ways that humans control chemical reactions in, say, a synthesis or chemical production setting, and we want to be able to describe those kinetics and then see how those things work so that way we can control them. All right, welcome to chapter 12, our first video done. We're looking for questions on participation 9/11, going to be due on Friday. And then as normal for our weekend assignments, we got the weekly homework due Saturday and the post-lab due Sunday. If you have any questions about anything, let me know. Otherwise, welcome to the set of videos. Welcome to chapter 12. Kind of cool, very different, novel kind of ideas, or different way to think about chemistry. If you have any questions, let me know.